We present DyLiN, a new state-of-the-art method that brings light field networks to the dynamic domain. Light field networks, the reformulations of radiance fields to oriented rays, are magnitudes faster than their coordinate network counterparts and provide higher fidelity with respect to representing 3D structures from 2D observations. They would be well suited for generic scene representation and manipulation, but suffer from one problem. They are limited to holistic and static scenes. Our method, the dynamic light field network, or DyLiN, can handle non-rigid deformations, including topological changes. DyLiN is also 25 times faster than HyperNerf at rendering, while having better scene reconstruction. This is particularly noticeable if we freeze the videos at the same time step. DyLiN more accurately models the coffee pouring, where HyperNerf seems to fail. We further introduce CoDyLiN, which augments DyLiN to the controllable scenario with controllable attribute inputs. CoDyLiN brings fine control over actions such as smiling, closing the eye, and raising the eyebrow, while being much faster at rendering than its competitors. I will now provide more extensive background information and details about our method. Novel view synthesis is a popular photometric optimization problem with the focus of synthesizing new, unseen views given a set of input images. Neural radiance fields, or NeRFs, proposed in 2020 by Mildenhall et al., are particularly good at this task. However, they are quite slow at rendering, taking approximately 3 seconds per frame. This is entirely an architectural limitation. Given a camera array, hundreds of points are sampled, and then each point is independently passed through an MLP to predict their respective colors. Then, every sample is numerically integrated to predict the ray color. Requiring hundreds of samples and MLP evaluations per array is the source of the high computational complexity. NeRFs have also been extended to the dynamic scenario. One such method, known as dNeRF, represents dynamic scenes with both a deformation network and a canonical network. The deformation network predicts the offset of a sample point xyz at time t, effectively bending the ray. After the offset is predicted, the bent ray is passed through the canonical network to predict the color and density of the deformed sample at time t. Similar to the standard static NeRF method, this one also requires hundreds of samples and MLP evaluations per array, resulting in a slow rendering time of about 8 seconds per frame. Most recently, light field networks, or LFNs, originally proposed in 2021 and later extended to the more complex scenes in the 2022 R12 paper, brought significantly faster rendering times to neural scene representations. Their method required only one sample and MLP evaluation per array, as opposed to the hundreds required by previous methods. Instead of predicting the color of an array with numerical integration of sample points, they could directly predict the color without the need for integration. Given a camera array, points are sampled and concatenated, and then passed through a deep residual MLP to directly predict the ray color. With the data-hungry nature of deep networks, they also rely on generating pseudodata from a pre-trained teacher NeRF to train the student on. While this method increased the efficiency of standard NeRFs, they have not yet been extended to the dynamic scenario. So, we thought, can we make this dynamic? The answer is yes, we can make LFNs dynamic, and this is the full pipeline for how we did it. We first train a dynamic teacher NeRF using real data from a given scene. Then, we synthesize pseudodata from the teacher, and finally, using both the pseudodata and the real data, we train our very deep dynamic student light field network that we term DyLiN. I will now introduce the full architecture of DyLiN. Given an array R with origin and direction and time t as input, we deform R and sample a few points along the deformed ray to encode it using the blue MLP. In parallel, we also lift the ray and time t to the hyperspace code W using the green MLP and concatenate it with each of the sample points. The concatenation is then passed to regress the RGB color of the ray at time t directly using the red MLP. To obtain this architecture, we directly extended the R2L light field network architecture to represent dynamic scenes. In specific, we added two MLPs. The first to offset the ray, and the second to learn a hyperspace for the ray given a camera ray at time t. DyLiN can handle both non-rigid deformations and topological changes while having an order of magnitude faster rendering time than previous methods. For HyperNerf to match the rendering speed of DyLiN, we require not just a 10 or 15 times improvement, but rather a 25-fold increase in speed. Our method is not just faster at rendering, it is also significantly better at preserving fine details such as the coffee pouring and the reflection on the chicken's eye. To best examine the visual performance of our method, the rest of the results in this presentation are played at the same speed with the actual FPS noted above. On this scene, DyLiN models the face, requisite the clothing, and arm motions better than both dnerf and tnovox, the previous state of the art. When freezing the videos at the same time step, this becomes far more apparent. DyLiN has a drastic increase in visual quality while rendering at near real time. In this result, we see DyLiN better preserving the black lines on the arm while also having smoother transitions. For the LEGO dataset, DyLiN more smoothly and accurately models the movement of the bucket than both dnerf and tnovox. In dnerf, the bucket appears to break apart during its transitions. While tnovox does not appear to have this problem, it is of significantly less visual clarity than DyLiN. Our method also models the platform texture much better than its competitors. To fully demonstrate the merits of our architecture, we developed two incremental baselines to compare to. For the first and most simple one, we remove both MLPs and directly add time t. By doing this, we see a noticeable drop in visual clarity from our full method. This drop in performance can be seen in how it represents the gum on the teeth and the fingers with the banana. The second, slightly more complex baseline we developed has the same two MLPs removed and time directly passed through as in the first baseline, but we also use a pointwise deformation MLP to predict the offsets jointly before regressing to RGB color. With increased complexity over the first baseline and an architecture closer to the full method, the results are better than baseline 1 while still not achieving the same clarity as the full architecture. It is also important to note that even our first and most simple baseline achieves better visual clarity than HyperNerf. One limitation intrinsic to all dynamic scene representations are that their transitions cannot be controlled. Take the jumping jack scene for instance. Finally controlling the movement of the arms and legs is not possible, as it is locked to the transitions at given time steps. However, there exist methods that allow for full, fine-grained control over an attribute's transition within a scene. We found that, with minor augmentations to DyLiN's architecture, we can extend it to this controllable scenario, with CoDyLiN. As shown in these results, we have complete control over the closing of the eye and raising of the eyebrow. To get the CoDyLiN architecture, we directly added masks to signify which regions of the scene are controllable, and attribute values for the state of the transition, with -1 being the start of the transition and +1 being the end. With the addition of both of these elements to DyLiN, we can fully control the smile, closing of the eye, and raising of the eyebrow. If you are interested in further details on this work, visit us at CVPR or check out our project page. Thank you so much for listening.